Thank you for the introduction. This presentation is a result from a collaborative work with Petrobras. Petrobras is the Brazilian oil company, so we granted those weldments for different welding process, versions of gas metal MIG process. Okay, the idea here is to work with short circuit metal transfer in MIG welding. I know someone may say, okay, that's not good. You may face lack of penetration. You have some sputtering. Although the qualification here is API 1104, there's no big down against short circuit metal transfer. But someone may say, okay, probably you suffer some effects. But at the same time, we have some advantage, low heat input. We can do positional welding. And more than that, welders like it. That pretty low radiation, makes life, the welder's life easier. So how do we try to cope with such limitations? Okay, of course, we try to do our best for proper adjustment on the welding parameters. We try to adjust inductance. We try to select suitable shielding gas. But at the same time, it could lead us to a narrow operational envelope, a very tight set of parameters. So what we intend to do and what we did was to select some derivative process in order to control the metal transfer and try to see if you reach a proper welding quality and sound weld bead. Of course, the idea of using those derivative process, and by derivative process here, I mean the ones that we control the waveform. Basically, here we use the Lincoln, Miller, and Fronius, STT, RMD, SMT, the most, let's say, famous on the market. We try to use that, but at the same time, when you use those parameters, you bring new difficulties because you have 3 or 4 parameters to be adjusted, sometimes 2, depends on the power source, to be adjusted in your new setup. So at the same time, you try to solve the problem, but you bring new challengers to that. So our idea here is to present how we determine those parameters and provide a set of suitable parameters or range of parameters for welding. And of course, at the same time, it's good for us because it demands higher professional knowledge. We get more well-trained. We keep going on researching on welding technology. Okay, there are different choices. As I said, STT, RMD, chop arc, SMT, cold arc, there are different options. Most of them based on the controlling the transfer, the metal transfer, the short circuit metal transfer by letting it happen by surface tension rather than electromagnetic pinch. So, okay, I prefer to call like that, such set of process. Is a MIG-MAG process with controlled short circuit metal transfer by using commercial power source. It doesn't matter, you select, by using some manufacturer. Sometimes we get lazy ourselves and we say, okay, it's an STT process, CMT process, RMD process. Indeed, it is not. It is a still MIG process, but with gas metal arc welding process, but with a waveform controlled power source. So sometimes we get lazy, but just to remind us that, let's say, a proper way of calling things. So the idea of this work is to carry out gas metal arc welding process over a small pipe diameter, API 5L X65. I know this is not a new steel, but it still has a lot of use in Brazil, especially the 65 and the 70, because we build small pipes up to 12 and 24 inches diameter. So the thickness is not that issue. So we still use a lot of 65 and 70. People are going for 80, X80, but definitely when you go for a larger pipe, 52 diameters, over 36 inches diameter, perhaps you should go for X100 or X110. Those are brand new materials. Okay, so We use API 5L-X65 with 8 inches diameter and 8 millimeters of thickness, less than 3/8. Contact import distance 12 millimeters, field wire conventional 1. Although someone may say, okay, you are using a class wire too close to your strength material of your base metal, so but still you can use that. Since it's a short circuit metal transfer, we use argon plus 25% CO2. We carry out some weldings with pure CO2, 100% CO2, and for root pass was all right, but for filling passes, it was not so good, so we just keep one shielding gas for the whole procedure. Okay, we try downhill with weaving, we try uphill with weaving, without weaving, and let's say one best productivity and best, we can reach a sound welding with less effort by using downhill with weaving. Here I'm just showing, let's say, the final set of parameters. For that thickness, 8 mils, we just use 2 passes. You don't need more than that. No backing, that's important. And we try to qualify in accordance to API 1104. We tried small length of the pipes. We placed 3 and we did 2 welds at the same time, 2 girth welds at the same joint. So in a set like that, we could run 4 weldments. That's a visualization of the joint. We use 15 degrees as bevel preparation. Someone again must say, okay, that's not good. You should have used, I don't know, 22, 25 perhaps. But the idea is to use a small amount of deposit material to go faster, to go as fast as we could. And 3 mils of root opening. We carried out macrograph, hardness, tensile, bending, nick break, and sharpie. I know some of them are not required by the APL 1104, but even though Petrobras required, okay, try to get as much as result from those weldings. As I said, we use different manufacturers, Lincoln, Miller, and Fronius. We use all those 3. Once the lady said that she received the SMT, the problem in Brazil that we have to buy all those 3. It's a shame for us, but it's all right. We try to compare those derivative process against conventional short circuit. Okay, where are you? Oh, here. Because conventional short circuit, you can have a very low cost power source. It's a very cheap power source. Of course, STT, SMT, or MD technologies, they have some aggregate value there. They need to be more expensive, of course. But let's see if we can weld with a low cost power source. This is conventional short circuit. Here's just samples of the signals that we got for conventional short circuit MIG welding. So we have current and voltage, the traditional, let's say, waveforms. And here for CMT, RMD, STT. So we see the trends that we expect, the pinch current, the drawback of the current, the metal transfer happening. So just to see, okay, we record the signal and we have all the voltage and current levels. Here's just a picture of, we also perform some, let's say, more fundamental work on that. We see here the conventional welding, here RMD, STT, and CMT. Okay, let's say conventional, you have more sputtering around, that's supposed to be expected. CMT, you have the up and down of the welding wire, as again the manufacturer says that would happen. So just to have a look that we have the same amount of material being deposited on the welding joint. As I said, we carry out by using downhill progression. The problem is they run out. Okay, getting weaker. We have the problem with the run out That's the major problem when you do a downhill position, no downhill progression, sorry. Here's just a set of the envelopes that we got for the root pass. Okay, basically it says, okay, you can weld with conventional MIG weld, you can weld with RMD, you can weld with STT, you can weld with CMT, you can weld with all of them. Here for root pass, we did pure CO2 and argon plus 25 CO2 with and without 1/16 of high-low. Okay, that's another issue. How much high-low you may have, in our case 1/16 is accordance to API 1104. So basically here, yes, we can weld with all those processes. Okay, some has a larger, more points to be welded, some smaller, but in that case we can weld with all of them. It's just that. In fact, that map here, that operational envelope, was carried out so you can weld both downhill and uphill. When you see every point here, you can weld both downhill and uphill progression. All right? But here in our case, let's focus on downhill. But that set of points says, okay, you can do full orbital weld with gas metal arc welding. Yes, you can do. All right? That's because you have perhaps 1 or 2 points only. That's because we did in orbital welding, full orbital welding, which means each point there you can weld downhill or uphill with no problem. But let's focus on the downhill here today. Okay, so that's just the setup we end for root pass and for filling pass. All the parameters are there. Peak current, base current, they all trim, arc control, arc length, dynamic control, each one for each manufacturer. That was the best we can achieve. So we left there on the paper. If you would like to take a look later, please, you are welcome. So that's what we can manage to achieve for both in root pass and filling pass. Right? If anyone needs to weld, that's it. Here's just a sample of the signals for conventional gas metal arc welding for all the 3 positions, flat, downhill, and overhead. 12 hours, 3 hours, and 6 hours, STT, RMD, and CMT. It's just to know that, okay, we record all the signals during all the process. Here's just to know that the welders, they know very well that when you change from uphill or from flat position downhill and overhead, you listen the frequency of the metal transfer being reduced. You start with high frequency, and the frequency of the metal transfer reduces when you reach 6 hours, which is overhead position. Here is some macros. You may notice that CMT and RMD free from defects. Here, STT, you have some lack of fusion, but we redid those sets were a previous set of macros. We have redone the tests, and we increased a little bit the current, and we had no more lack of fusion for STT. It was perfect. But for conventional welding, we got a nice route, but we didn't manage to not let that lack of fusion. In all runs, we got this lack of fusion here in the downhill progression, all right? But for STT, no. That's just an old macro that I present here. Okay, someone may say, okay, what about that underfilling? According to API 1104, yes, you can have underfilling if it has a good concordance here. If you don't have a really a burn or undercut. If you have undercut, no. But in that case, if you look at the weld bit, you see that's a good concordance here. You have a smooth profile over here. So by macros, you would say, okay, those derivative process are approved. Okay, again, this is just a localized problem. We have redone that. But for conventional gas metal arc welding, we got some issues on the filling capping pass. For the root pass, no, you can do that perfectly for conventional welding. This material X60, normally it doesn't have any, let's say, metallurgical problem. From micro hardness measurement, most of them less than 200 Vickers with 0.5 kilogram force, and even here in that high point is 250. Normally API 1104 says it should be under 350, 310, if I'm not wrong. So from the micro hardness, we got no problem. But again, it's a very easy material to be welded from the metallurgical point of view. Tensile test, no problem, everything approved. So we just got all the fracture out of the weld bit, no problem at all. But for the bend testing, yes, that problem with lack of fusion appear here. So you see a fracture here for the conventional gas network welding. The other two, no. For STT in our previous test, yes. If you have that lack of fusion, you end up with problems in your bend testing. But once you correct that lack of fusion, you don't have any problems in your bend testing. So up to now, all those three processes are approved, but the conventional one, no. We got some problems in the macros, and here again we got some problems in the bending tests. That's why I like so much bend testing. Nick break, because I mean, even 1104, API 1104 says nick break. Once you have an let's say a mechanized process, you wouldn't have any problem. We did nick break testing, but we look in the fracture and we got no pores, no slag inclusion, nothing like that. So nick break was just let's say a pro forma. Nothing new came out of that. We also did some V0 Sharpie test. Here's the coupon and all the energy. This was for 0 degrees centigrade, which is 41 Fahrenheit, right? Yes. Because in Brazil we don't have -20, -40, so 0 degrees is enough for us. So all the absorbed energy is well away from 40 joules, which is required in our case. 40 joules, so you are here for 150, 100 joules, so way. But again, because the material, we did expect any metallurgical problems. So here, Sharpie, the V0 test says, V0 says that again. Again, metallurgically, we see the micrographs on base metal, heat effect zone, weld metal, just ordinary, let's say, pyrolytic structure. So nothing new. Really weighted structure that we may have here. Nothing really new. No grain growth. Not much martensite. You don't see martensite here, but nothing really special. It's just to say, okay, it's good. We know that's good. It's good. Okay. So I'd like to withdraw some conclusions. In accordance to API 1104, we got sound welds obtained for all investigated process. Is not completely true. We got sound weld. I should have changed that because it was for root pass. Yes, for root pass, we got sound welds for conventional CMT, STT, RMD. But for filling pass and cap pass, we did not manage to solve the problem for conventional gas network welding. So that is an indication that yes, perhaps it's good to use those derivative process instead of conventional gas network welding. For root pass, we managed to solve that. For filling pass and cap pass, no. We did not manage to use only conventional gas network welding. We had to go for derivative ones. Okay, in the paper you may find the different operational envelopes. Please, if you look, take a read, or if you need those parameters, you'll find in the paper. And we reach travel speeds up to 35 centimeters per minute, which is roughly 5 is 10, 70, okay, maybe 10, 12, 15, let's say 15 inches per minute. Why we stick in those values? 12, 15 meters per minute, because although we did everything mechanized, Petrobras wanted a set of parameters to be welding by welders. So we did not push too much welding current. Otherwise, you need to go too faster, and the welder cannot go too faster. Because in Brazil, we have an issue. Okay, you need to mechanize, you need to automatize your process, but still you need to keep the welder's jobs, right? So our project was how much I can go and up to 35 centimeters per minute, which is roughly 15 meters per minute, 12 meters per minute. So, okay, you can weld mechanized, but if you need the welder also can follow that speed. That was the let's say, the limit of our work. And we have a lot of works ongoing, different welding joints to solve the problem, especially for J preparation. We have tried that also on duplex stainless steel. We use vision system, different control system that we have used to try to use conventional gas metal arc welding and try to solve the problem. Thank you very much for your time.